Hi students, let us continue with the signed and unsigned integers. So in the previous video I explained about the unsigned integers. Now let us see what is the signed integers. So the signed integers is a representation of signed int numbers. Okay, it can be represented in several possibilities. So that I explained that it can be represented in sign magnitude, or it can be represented by using 1's complement, or it can be represented by using 2's complement, or you can go for excess n bias, or it also represent by using the BCD, binary coded decimal representation. So these are the different ways that you can represent the signed numbers. So unsigned means only it follow one method, because it is only the positive numbers it will take. So the unsigned range is between 0 to positive infinity. Okay, so it is the range between 0 to positive infinity. Whereas signed integers, it follows the negatives also, the negative as well as the positive. So these signed numbers can be represented by using sign and magnitude, 1's complement, 2's complement, excess n bias, and the BCD, binary coded decimal. Now let us discuss one by one in the signed integers. So first I'll take sign and magnitude. So what is the sign and magnitude? The name itself is saying that sign is a number, that is a positive or a negative number, and the rest of the numbers are the magnitude you call. Let me write that point. Leftmost significant. Leftmost significant bit represents the sign of integer, and remaining bits represents magnitude. So what it means? It is saying that the leftmost significant bit, what do you call this leftmost significant bit? So if you take any binary number, suppose I have taken 0, 0, 0, 0, 0, 1, 1. So this is a 7. The 7 decimal, and the binary number is the 7. So here the leftmost, this is the leftmost significant bit. You call it as leftmost significant bit, because this is in left side. So the leftmost significant represents the sign bit of integer, and the remaining you call, the remaining bits you call it as a magnitude. So this represents the sign, and this is magnitude. Okay, so that's why we call it as a sign and magnitude. The leftmost bit is sign, and the remaining bits is magnitude. So sign and magnitude. Suppose if it is 0, the sign bit, the leftmost bit is 0. If it is 0, then the number is positive. So if this is 0, the sign bit is 0, then number is positive. Suppose it is 1. The sign bit, suppose this is like this. Okay. So if the leftmost significant bit is 1, then the number is negative. Then you can say that number is negative. So this you call it as a sign and magnitude. So the sign and magnitude will be based on the leftmost significant bit. That represents the sign of an integer, and the remaining all bits represents the magnitude. Okay. And it is the simplest for humans to understand this concept. So whenever you have seen this binary number, if suppose the leftmost bit you have seen it is 1, you have to think that it is a negative number. If it is 0, you have to think that it is a positive number. So for humans understanding, make it as clearly understand by the humans, they make it like this. But this sign and magnitude is somewhat costly to implement also. Now let us see examples, different examples. I'll take 2 examples here for this sign magnitude also. First example 1. So the same, store So whenever the plus or minus is represented before the decimal number, you have to think this is a sign integer, whether it is a sign positive or negative, whatever it may be. So whenever a plus or minus is indicated, you represent it is nothing but a sign integer. Suppose simply a number is there, the 7, like that 7 or 16 or 254, like that some simply numbers are there, those numbers are represented as unsigned integers. That you have to be remembered. If anything is there between before the number, then it is signed integers. You have to call that numbers as a signed integers. So store plus 7 in an 8-bit memory location using sign and magnitude representation. By using this representation, I want to store the number 7 plus 7 in an 8-bit memory location. So any bit pattern you can follow, any representation you can follow, means the system can follow. That system can follow any representation based on that system configuration, that CPU configuration. Based on the CPU configuration, the storage of the bits can be followed any type of representation. So I'm explaining different types of representations of integers. So store plus 7 in an 8-bit memory location using sign and magnitude. So let us see the solution for this, how we'll store. So the first thing is, first change the number to binary. So the 7 binary number is 111. Now I have to add 5 zeros. Not instead of 5 zeros, here I'll add only 4 zeros. Why I add 4 zeros? I'll explain that. Add 4 zeros to make total of n minus 1 of 7 bits. So I want to make it as only 6 bits location. So that is 1, 2, 3, 4, 1, 1, 1. So now what is the total numbers here? Total bits are here 1, 2, 3, 4, 5, 6, 7. Only 7 are there. But our memory location needs 8-bit memory location. So instead of adding 5 zeros, I am added only 4 zeros up to n minus 1 location, not n location. N minus 1 location I make bit as a n minus 1 location. So because I have to make the last leftmost significant bit represents the sign magnitude. So here add an extra 0. I had to add an extra 0 because the number is positive. So if the number is negative, minus 7, I add 1 here, an extra 1 here to make it as a negative. The leftmost significant bit, if it is 1, it is negative. If it is 0, it is positive. But here in the problem, it is plus 7. So add an extra 0 to the leftmost significant bit because the number is negative. Then what will be the result? The result is, so I'm adding extra 0 to this number and complete this number 1, 2, 3, 4, 1, 1, 1. Then what will be the total bits here? 1, 2, 3, 4, 5, 6, 7, 8. So now this 8-bit data is stored in memory location. I hope you understand. So here I have taken plus 7. Now I'll explain with sign magnitude minus. So how the data is stored if it is a negative value. Okay. So store minus 258 in 16-bit memory location using sign and magnitude representation. Let us see the solution. So first step is the common. The first step is change number to decimal, sorry, binary. So this is 255 is already a decimal, so you have to change this number to binary. So the binary number of 258 is 1 0 0 0 0 0 0 1 0. So you just convert into by taking the LCM, okay, like this. So if you do like this, you will get this binary number. So now the second step is add 6 zeros. Add 6 zeros to make a total of n minus 1 15 bits. Okay, so I want to make it as a 15 bit, but the last means the leftmost significant, that is a 16 bit, is represents the sign magnitude. So I'm just adding 6 zeros to make it as total 15 bits. So now add this 1 2 3 4 5 6 1 1 2 3 4 5 6. So here how many binary numbers are there? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So total 15 bits are there, but I need 16-bit memory location, means I have to convert that number to store in the 16-bit memory location. Now add extra 1. Why am I adding extra 1? Because here this is negative. The number is negative. Negative means the leftmost significant bit should represent 1. So add extra 1 because the number is negative. So then what will be the result? The result is, so you have to add 1 1 2 3 4 5 6 1 1 2 3 4 5 6 1 6. So this is complete 16-bit numbers. So minus 258 is converted into 16-bit numbers. Now it is stored in memory location. So this is about the sign magnitude of signed integers. Thank you.